Okay, in today's lecture we're going to start our Chapter 1 material on linear equations in linear algebra. So the primary goal of our course, or a lot of the applications that we'll be dealing with throughout this course, involve solving a system of linear equations. So in this first chapter we're going to define linear equations, systems of linear equations, introduce some techniques for how to solve systems, see what types of solutions we might have for a given system, and talk about some applications. So in our first section, 1.1, we will talk about systems of linear equations. This will just be an introduction where we introduce some definitions and consider how to solve a given linear system. So let's start with defining what exactly a linear equation is. So we would say a linear equation in the variables x1, x2, up through xn is any equation which has the following form. It is the sum of a1 times x1 plus a2 times x2 plus a3 times x3 and so on up through an times xn is equal to b, where these values a1 through an and b are constants, and a1, a2 up through an are called the coefficients for that equation. It's the numbers that appear in front of our variables, x1, x2 up through xn. And our subscript that we're using here in can be any positive integer. So we can have a linear equation in a single variable, 2 variables, 3 variables, up through any finite integer, positive integer value number of variables. And in a lot of applications in the real world, we might have linear equations involving maybe 500 or more variables. Throughout our course, we'll only consider systems of maybe up through 5 or 6 variables at most. So what we mean by a system of linear equations would be just a collection of more than one equation which involves the same variables. So let's say that we have a linear equation in n variables. So we have our first equation here, constant multiples of x1, x2 up through xn. And if we sum those values, we have this as equal to some constant b1. And then let's say that we have more than one equation. So let's say we have a second equation, also in linear, involving the variables x1, x2 up through xn. And we have different coefficients for each of those variables, and we take their sum, we have a different constant b2. Up through, maybe we have m equations altogether involving the n variables x1, x2 up through xn. So any collection of more than one linear equation which involves the same variables is said to be a system of linear equations. So here again, for a system, x1, x2 up through xn are variables. Each of my coefficients, which is denoted here as a sub ij, so that was these constants a11, a12 up through a1n, then a21, a22 up through a2n, and for our last equation, am1, am2 up through amn. So these are constants, and of course our right-hand side of the equation, these values b1, b2 up through bm are also all constants. So when we are looking at a system of linear equations, our goal is to find a solution. So what exactly do we mean by a solution? Well, a solution of our system is an ordered list of numbers, s1, s2, up through sn, which are all real numbers. So this would be a vector of length n with real numbered entries. And this list of numbers would satisfy all of the equations in our system. So we're looking for what are the variables x1, x2 up through xn, such that if we were to substitute those variables into each of our equations in the system, it would make it true. And whatever the values are that we have for those variables, say if x1 is some number s1, x2 would be a number s2, up through xn would be some number s sub n, and that collection of numbers for each variable which satisfies the system would be called a solution of that system. Now, for systems of linear equations, it's possible that we might have more than one solution. So we refer to the set of all possible solutions of a system as the solution set of that system. And throughout our course, when we are trying to solve linear systems, the general process that we'll use to solve them is to manipulate them to convert our system into an equivalent system, which is a little easier to solve. So what exactly do we mean by equivalent systems? Well, we would say that two linear systems are called equivalent if they have the same solution set. So if we find a solution of one system and we have an equivalent system, then our solution that we found for the first system would also solve that equivalent system. So at first glance, this seems a little messy. It seems very technical right from the beginning. Well, okay, maybe, I mentioned we might have up through 500 variables or something possible. And this language, this new terminology, systems of linear equations and solution sets might seem a little daunting. But we've actually been working with systems of linear equations since your high school algebra days or geometry days, and up through your calculus courses, you've already seen systems of linear equations and how to solve them a little bit. So to introduce our discussion for how to solve a linear system, let's consider a familiar problem, maybe the easiest case where we have a system of two linear equations involving two variables. Say our variables are x1 and x2, and we have two different linear equations involving those two variables. So these linear equations, in terms of two variables, geometrically define lines. So here, each of these equations represents a straight line in the plane. Here we would be talking about the x1, x2 plane. Or if we preferred, instead of saying x1, x2, we might use x and y, and think about this as these equations as defining straight lines in the xy plane. So what we're looking for to find a solution of such a system would be a point s1, s2, so that is some point in the x1, x2 plane, that satisfies both of these equations. So geometrically, what we're talking about for a solution would be any point of intersection of the two lines. So geometrically, we can consider that there are three cases for what our solution set might look like. So one possibility is that our system has exactly one solution. That is, our two lines, which are given by the equations, have a single point of intersection. So we've illustrated that case in our figure below here in this leftmost plot. So let's say we have two lines, one which is the graph of our first linear equation, and another which is the graph of our second equation. And we see here that they have a single point of intersection. Now, another possibility is if our system of equations, or two equations and two variables, define lines which are parallel. So we could have a system that does not have a solution if our two lines are parallel. So if our lines have the same slope, but different y-intercepts, then we might have two lines which never intersect, in which case there is no point that would satisfy both of our linear equations. It would not have a solution. And then our last case for a solution of such a system is that we have infinitely many solutions. And that would arise in the case that our two lines are identical. So if we had two different equations for the same line, maybe one is just a constant multiple of the other, then we would have two lines with the same slope and the same y-intercept. So in other words, our two lines would be identical, and every single point on that line would be an intersection of the other line. So we would have every point on our line as a solution of our system, and since there's infinitely many points on a line, we would have infinitely many solutions. So a little more terminology before we look at solving some systems like this. With regard to our different cases for the type of solution we have, we could say that a system is either consistent or inconsistent. So we would say that a system of linear equations is consistent if it has a solution. That is, if it either has one solution or infinitely many solutions. So if there is at least one point of intersection of our lines or one solution of our system of equations, that system is said to be consistent. Whereas a system is called inconsistent if it has no solution. That is, if there is no point of intersection of our two lines, or in the case of equations in more than two variables, there is no point that satisfies all of the equations in our system. And we would refer to that type of system as inconsistent. So now that we've introduced a lot of this terminology and defined a system of linear equations and a solution, let's look at some examples for how we could solve simple linear systems, say just involving two variables, and illustrate these different types of solutions that might arise. So in our next several examples, we are given a system of linear equations involving just two variables, x and y, and we're told to solve each of these linear systems. So really, each of our examples here, we're asking what is the point of intersection of the two lines whose equations are given. So let's look at this first one. In our first one, we are asked to solve the linear system defined by x minus y is equal to -2 for our first equation, and 2x plus 3y equals 6 for our second equation. Now, there's several ways that we could go about solving this type of system. The solution that you typically saw, say in your high school class or maybe pre-calculus courses, would be to solve one equation for one of the variables, maybe solve our first equation to get x in terms of y or y in terms of x, and then plug it into the second equation to reduce it to a single variable. And then we can solve that single equation for our one variable and back substitute to get our other variable. So that's, of course, a valid technique that we could use, but when we get to systems of more than two equations or more than two variables, that substitution method becomes much more difficult to implement, very time-consuming. So to sort of segue into the approach that we'll discuss a little bit later in this section, let's think about solving this system in the following way. Intuitively, I want to get rid of one of my variables. I want to reduce my system of equations involving two variables to a single equation only involving one variable. So that is, I want to eliminate the variable x or the variable y within this equation. So one way that we could do this would be to try to eliminate the variable x first. So notice if I look at my two equations, the coefficient of x in my first equation is 1. I've got 1x, And in the second equation, I have 2x. So if I wanted to think about killing off the variable x, if I want to get rid of this x term, one way that I could do it would be to multiply my first equation by a -2. I know that if I were to multiply both sides of my equation by some constant, it represents the same line. It doesn't change the equation. So if I were to multiply my first equation by -2, it would become -2x plus 2y is equal to +4. And my second equation, if I leave it alone, was my 2x plus 3y is equal to 6. So now that my coefficient of x are both 2, one positive and one negative, if I wanted to eliminate the variable x, I could think about adding these two equations, and I would be left with a 5y is equal to 10. My plus 2x and minus 2x, when I take the sum of these equations, cancel, and I'm left with a single equation involving y, which I can easily solve. We see from here that y would have to equal 2. And now once we have the value for y, we can plug into either one of our earlier two equations to find the x-coordinate for the point of intersection. So let's see how we could do this. If we work with our first equation in the system, we had x minus y, which we found to be 2, has to equal -2. So solving for x, if we add 2 to both sides, we find x is 0. So here we find that there is one point of intersection for these two lines, the point x equals 0, y equals 2. So here we could say there is one solution, namely the point xy equals 0, 2. So for this first system of two equations and two variables, we saw one solution. And actually for this example, that pair of lines is the pair of lines that was illustrated here. We see the point of intersection of those two lines was 0, 2. So let's look at another example. In our second example, we are asked to solve the linear system, 2x plus 3y equals 6, and 4x plus 6y is equal to 4. So we could approach this the same way that we did in our first example, by trying to maybe eliminate the variable x from both equations. So if I look at these two, I have a coefficient of 2x in my first equation and 4x in the second equation. So one way that I could eliminate the variable x from this system would be to take my first equation, multiply through by -2, so that I would have a -4x, and then if I were to add that to the equation below, I could cancel out my x variable. So let's look at this. If we indeed multiply our first equation through by -2, we would have -4x minus 6y is equal to -12. And the second equation was 4x plus 6y is equal to 4. So now that we have the same coefficient, just with different signs for our x variable, if I were to sum these two equations, my plus and minus 4x will cancel. And now notice also for this example that our coefficients of y are negatives. We have -6y and plus 6y. So when I take their sum, I'm left with 0 on the left-hand side. And on my right-hand side, if I take the sum of -12 and 4, I have -8. So what we're finding is that in order for these two lines to have a common point of intersection, we would have to have the equation 0 is equal to -8 hold. Now, of course, we know that 0 cannot equal to -8. So that means that these two lines do not intersect. And in fact, when we look at their initial equations, we can see that our second line has the same coefficients as our first line, but just scaled by 2. In our y-intercepts, these constants on the right-hand side are going to be different. So we have here parallel lines, which are not intersecting. So here we have no solution, or we might say, using our new terminology for linear systems, the system is inconsistent. So when we say that a system is inconsistent, that means that there is no solution, or equivalently, if we have a system with no solution, we could say that that system is inconsistent. So let's look at our last example for a system with two variables. So here we are again told to solve the linear system defined by 4x plus 6y equals 12, and 2x plus 3y is equal to 6. So if we try to approach this the same way, well, we could try to eliminate the variable x by getting the same coefficient for x in our first and second equation. So if I wanted to have maybe a 4x for my first and second equation, I could multiply my second equation through by a 2, or a -2, and my first equation is 4x plus 6y is equal to 12. And if I multiply that second equation by -2, I have a -4x minus 6y is equal to -12. So at this stage, notice that these two lines are actually identical. The first and second equation are identical, they're just negatives of each other. So if I were to multiply my second equation through by a -1, they really define the exact same line. So before proceeding further, we can say here that these two lines are identical, or these two equations define the exact same line. So let's see what happens here algebraically. If we were to sum these two equations, our positive 4x and -4x cancel, our positive 6y, -6y cancel, and we're left with 0 for our left-hand side. And then on the right-hand side, summing our positive and -12, we have 0. So we see here that 0 equals 0 for every choice of x or y. That equation always holds, whereas in our second example, we had 0 had to equal some non-zero constant. There was no solution. In this example, 0 is always equal to 0. And we see that we actually have two equations which define the exact same line. So we're working in the third case where we have infinitely many solutions. So here, let's say we have infinitely many solutions. And in the case that we have infinitely many solutions, usually the way that we try to characterize those solutions, or that solution set for the system, is by making use of what's called a free variable. So we're trying to define or come up with a way to express every single point on this line as a possible solution of our system. And one way to do that is to make use of a so-called free variable. So since these two equations are identical, I'm allowed to choose one of my variables, either x or y, as anything I want. That is, I'm free to choose it as any number. So we would call that variable a free variable. So in this example, let me take x to be any number that I want. And in your textbook for this course, which is the notation that I'll stick with in my notes, they use the notation t for their free variable. So let's make a choice of our variable x as some real number t. We will say this will be a free variable. And then I need to know how y is defined in order to define a point on this line. So once I make a choice for the variable x, well, it needs to satisfy the equation of our line still, x and y. So let's see if we can solve for y in terms of x to get our solution set. So maybe working with our second equation in the system, we had 2 times x. Now x we chose to be some constant t, a free variable, plus 3 times y has to equal 6. So solving for y, we have 3y is equal to 6 minus 2t, or dividing through by 3, I have y is equal to 2 minus 2/3 t. So the way that we would write our solution of this system, in the case that we have infinitely many solutions, would be in the following way. We could say the solution set is the set of all points x, y, where x we chose to be t, and y was given by 2 minus 2/3 t, such that t was a free variable. That is, t could be any real number that we want. So here we have infinitely many solutions, which would be points lying on the given line, and any point which lies on this line would be written in the following form: t and 2 minus 2/3 t, where t is any real number. So again, in that last example, in the case that we have infinitely many solutions of a system, we introduce what's called a free variable. That is, we make an arbitrary choice for one of our variables and then solve for the other variable or variables in terms of that free variable. So in our first examples here, we are seeing that we can maybe multiply one of our equations by some constant and add or subtract them in order to reduce our system to a single variable, and then solve solve our single equation for that variable and then solve for the other variable by substituting into a previous equation. So this method, which we've outlined in our first few examples, is a fairly efficient method for solving larger systems of linear equations, say involving 3 variables and 3 equations, 4 variables and 4 equations, or so on. So let's see if we can make this process that we've been using in our first few examples a little more formal. So in general, when we talk about solving a linear system, our goal is to transform the given system into an equivalent system, that is, one with the same solution set, but which is easier to solve. And the way that we try to accomplish this is by performing what are so-called elementary operations on that system. Now there are 3 elementary operations which we can perform on a linear system to transform it into an equivalent system. The first elementary operation is that we can multiply any equation we want by any non-zero scalar. So any equation that I have, I can multiply it through by any non-zero number that I want, maybe to get the same coefficient for one of my variables. Let's say we want the same values for x, so that I could add or subtract my two equations and get rid of that x variable. So we saw that in our previous three examples. Another elementary operation which we can perform is that we can replace any equation by the sum of that equation, that is the sum of itself, and a multiple of another equation. So like we were seeing in our first few examples, maybe after I multiplied one of my equations by a constant, I would add those two equations in order to kill off a variable and reduce to a single equation and a single variable. So this is another elementary operation. I can add or subtract multiples of any two equations that I want, and I have an equivalent system. And our last elementary operation is that I can interchange any two equations. So I can rewrite them in any order that I want. Like if I were looking at one of my previous examples where we have two equations and two variables, if I were to reverse the order in which I wrote those equations, it would still be the same system, the same set of lines. So that third operation is that we can interchange any two equations we want, and we will not change the solution of that system. So this process of performing elementary operations to a linear system to get an equivalent system, which is a little easier, is known as Gaussian elimination. So this process of performing those elementary operations to obtain a solution of a system is what's called Gaussian elimination. And we saw some examples of this in a system of two equations and two variables. So in our next examples, we'll consider a little bit more complicated case. Let's say that we have three equations in three variables. So in this first example, we are asked to solve such a system. We see here that we have three linear equations involving the three variables x, y, and z. So we are asked to solve this system and then interpret our solution geometrically. So in the case that we were working with earlier, where we had two equations and two variables, each equation was defining a line in the plane. Now you know from your Calculus 3 course that a linear equation in three variables, x, y, and z, defines a plane in space. So here, this system of equations that we have is describing three planes in space. And when we're trying to find a solution of this system, we're asking ourselves, well, is there a point of intersection of all three of those planes? Is there some point that lies on all three? So in order to solve this system, we're going to perform Gaussian elimination on it. And in my first step here, let me just rewrite the system that we're given down here. My first equation was x plus y minus 2z is equal to -3. Our second equation was 2x minus 3y plus z is equal to -1. And our last equation was 3x minus 2y plus z is equal to 2. So at this stage, we start to see, well, if we tried to use the approach that you might be familiar with from, say, your algebra class, where you could solve for one variable in terms of the others, that starts to get a little more tedious as soon as you introduce a third variable. So maybe I could solve my first equation for x in terms of y and z, plug that into the lower two equations to get two equations and two variables, and then repeat that process. But we start to see that that gets pretty tedious. So instead, let's see if we can perform this process of Gaussian elimination to get an equivalent system. So let me start by introducing some notation that we're going to use when we perform Gaussian elimination. So this system of three equations that I've rewritten here that we were given in the problem, we're going to say is equivalent to a simpler system. And the notation that we use for equivalence of systems is a tilde, sort of an elongated tilde symbol for equivalence. And let's see what elementary operations we could perform on the given system in order to simplify it. So if we sort of follow our work that we did in the previous examples, maybe I could try to eliminate one of my variables, x, from our system. So if I think about my second two equations here, they have a coefficient of x as 2 and 3, and my coefficient of x in the first equation was 1. So what I'm going to try to do is use this first equation, where my coefficient of x was 1, to kill off the x variables in the second two equations. So if I wanted to kill off the 2x term in my second equation, one way that I could do that would be to multiply my first equation by -2, so that I would have a coefficient of -2x, and then add it to the second equation to kill off that positive 2x. Now, the notation that we would use for that operation would be the following. So typically either above or below this tilde symbol that I've written for equivalence, I'm going to keep track of what operation I'm performing. So here, the operation that I was describing is that we could take our second equation, we might denote that as E2 for our second equation, and from that second equation, I'm going to subtract 2 times the first equation. Or equivalently, I'm multiplying my first equation by -2 and adding it to my second equation. So I'm not going to make any change in my first equation just yet. I still have x plus y minus 2z is equal to -3. Now, when I perform this operation, take my second equation and subtract 2 times the first equation, let's see what that second equation reduces to. So I would have a -2x plus 2x gives me a 0x. Then multiplying my first equation by -2, I would have -2y plus my -3y leaves me with -5y in that second equation. And then doing the same with my z variable, if I multiply -2z by -2, that gives me a positive 4z, and then I'm adding it to that second equation where I had 1z. So my 4z plus 1z gives me plus 5z, and that's equal to, if we perform the same operation on that right-hand side, well, if I multiplied my first equation by a -2, I would have a positive 6, and then I'm adding it to that equation below it. So I would have a positive 6 minus 1 leaves me with a positive 5. Now, in this same step of Gaussian elimination, I want to try to eliminate that 3x variable in my last equation. So that is, I might want to use my single x, 1x in the first equation, to kill off this 3x in my third equation. And one way that I could accomplish that would be to take my third equation, E3, and subtract from it 3 times the first equation, E1. Or equivalently, multiply my first equation by a -3 and add it to the third equation. So let's see what we get when we do that. If I take a -3 times my first equation, I have a -3x, and then with my plus 3x, we see the x variable disappears. And then moving to our y variable, if I multiply my first equation by -3, I would have -3y plus the -2y gives me a -5y. And then for my z variable, I would have -3 times the -2z gives me +6z plus my 1z from the third equation, which would give me 7z, is equal to, let's see what happens with our constants. When we take -3 times our -3, we have a +9 plus the constant 2 from our last equation leaves us with 11. So this new system that I have here is equivalent to the first system, but notice that my second two equations don't involve x anymore. So my last two equations are now two equations just involving two variables, y and z. So we've reduced it to the sort of examples that we were considering previously, where we just had two equations involving two variables. So if we were to use that same approach to further simplify this system, maybe I could eliminate the variable y or the variable z in one of those later two equations to get down to a single variable. And we can do that by performing these elementary operations, that is, by performing Gaussian elimination. So the system that we just have reduced to is then equivalent to the following system. So my first equation, I'm still not going to change. I still have an x plus y minus 2z is equal to -3. And one thing that I might do here, let's leave it alone for now. I'll leave my second equation alone. Let's say I have a -5y plus 5z is equal to +5. And then let's think about what operation we could perform to kill off the variable y in my last equation. So looking at the coefficients for y in my second and third equation, well, we notice that they're identical. We have a -5y and a -5y. So if I were to take the difference of those two equations, our y term disappears. So what I could do would be to take my third equation and subtract the second equation from it. That would be e3 minus e2. So my last equation, well, the -5y minus a -5y cancels the y variables. And then we have a 7z minus 5z, which would leave us 2z, is equal to, when we subtract our constants, we have 11 minus 5, which would leave us with 6. So we have the following system, which is equivalent to the system we started with, and we have now reduced our third equation to a single variable. So we could solve it immediately there if we were to divide that second equation through by 2. We find from our last equation that z has to equal 3. Now, once I know z, I still need to know x and y. So how could I obtain x and y? Well, if I know z, the second equation gives a relationship between y and z. So I could substitute into that second equation the value for z that I found, and then solve for y. So we can go ahead and do that here, or I'll mention one thing that we might consider doing before substituting z into that second equation is we could simplify our second equation a little bit. Notice that the coefficient for y and z and our constant on the right-hand side all involve 5. They're all either plus or minus 5. So to simplify that second equation, I could perform another step in Gaussian elimination. I know I can multiply any equation by any non-zero number that I want. That was the first of our elementary operations. So let me take my second equation and multiply through by 1/5. So that is taking 1/5 of equation 2. We have our first equation is still x plus y minus 2z is equal to -3. Taking 1/5 of our second equation, we have -y plus z is equal to 1. And then my last equation, really to solve for z, I'm dividing both sides of that equation by 2. So if I were to take, say, half of that third equation, I would have just z is equal to 3. So at this stage, we see that z was equal to 3. And then to find y, I can take that z value and plug into our second equation. So this gives me -y plus z, which was equal to 3, we know has to equal 1. So we have -y is equal to -2, or y is equal to 2. And then to solve for x, we could go back to our first equation in the system, which has remained unchanged throughout. So here we would have our first equation is x plus y, which we found to be 2, minus 2 times z. Now z was equal to 3, so we have -6 has to equal -3. So equivalently, x minus 4 is equal to -3, or x is equal to 1. So our solution is a single point. So we could say thus, there is one solution, namely the point x, y, z is equal to 1, 2, 3. X was equal to 1, y was 2, z was equal to 3. Now, the last part of our example, after we were told to solve this system, it said interpret our solution geometrically. So what does this mean geometrically? Well, that means that there is one point of intersection for the 3 planes whose equations were given in the example. And the point of intersection on those 3 planes is the point 1, 2, 3. So in general, for any linear system, not just systems of 2 equations and 2 variables, there are 3 possible solution sets. We can either have exactly one solution, we can have infinitely many solutions, or no solution. That holds for linear systems in general, no matter the number of equations or variables. So let's look at 2 other examples that illustrate the other cases of solutions for linear systems in 3 variables and get a little more practice with this Gaussian elimination process. So in our next example, we have the exact same sort of problem. We are told to solve the linear system given here. 2x plus 3y plus z is 1, along with our other 2 equations. So linear equations in 3 variables are again defining geometrically 3 planes in space. And the question is there a solution? Is there some point of intersection of all 3 planes? And then for whatever our solution is, we are supposed to interpret that solution geometrically. So let's see if we could solve this system by reducing it to a simpler system by performing Gaussian elimination. So again, my first step here might just be to rewrite our system. So we had the system 2x plus 3y plus z is 1. Our second equation was x plus y plus z is 3. And our third equation was 3x plus 4y plus 2z is equal to 4. And let's think about operations that we could perform here in order to simplify this system. So my personal preference here, there's several different ways that we could simplify this system using our elementary operations. And my personal preference is always to have my first equation in the system have an x coefficient of 1, if possible. So there's a couple of ways that I could go about getting a 1 coefficient for x in my first equation. One possibility would be to just interchange my first two rows, or my first two equations, equation 1 and equation 2. Another way that we might be able to do it, we see that the coefficient for x in our first equation is 2, so we have 2x. If I were to subtract the second equation from that, my 2x minus 1x would give me a single x in that first equation. So the point that I want to make there is that there's a number of ways that we could go about performing Gaussian elimination. What you might do for your solution may not always match step for step the solution that I would give or another student's, which is why I require you to illustrate at each step of Gaussian elimination what operations you're performing. So here, to illustrate my preference, I would say that this system that I'm given is equivalent to the system that I would get by interchanging my first two equations. So the way that I might write that is, let's take equation 1 and equation 2 and swap them. So when you are presenting your solution, your written solutions to exams or quizzes or any written work that I have you do for the course, always be sure to indicate what operations you're performing with your equation from step to step, because what you might be doing is different from what I would do or another student does. And if you don't write which operations you're performing, it's a little hard to check your work from step to step. So performing this operation, just interchanging my first two equations, I have my first equation is now x plus y plus z is 3. My second equation is now 2x plus 3y plus z equals 1. And my third equation is 3x plus 4y plus 2z is equal to 4. So in performing this step, I now have a 1 coefficient for x in my first equation. Now, the reason that I like to have that 1 coefficient for x in the first equation is I can now use that 1x to kill off any constant multiple of x that I have in my second equation or third equation. So proceeding in the same sort of way that we did in our last example, if I wanted to kill off the 2x in my second equation, one way that I could do it would be to multiply my first equation by -2 and then add them. So to illustrate that, we could say this system is then equivalent to the system we get by taking our second equation, e2, and subtracting 2 times the first equation, or equivalently multiplying the first equation by -2 and then summing them. So our first equation is x plus y plus z is equal to 3. We haven't made any change yet in that first equation. Now performing this operation, well, we have a -2x plus 2x cancels the x in our second equation. Multiplying our first equation by -2, we would have a -2y plus 3y, leaves me with 1y in the second equation. Multiplying the first equation by -2, we have -2z. Then when I add that to the equation below, we have plus z, so we have -z left over. and that is equal to, performing this operation on the constants on the right-hand side, what we would have -2 times 3 is -6. Adding that to the constant 1, we would have -5. Now, in the same step, if I want to kill off the x variable in my third equation, the 3x, one way that I could accomplish that would be to take my third equation and subtract 3 times the first equation, or equivalently, multiply my first equation by -3 and add to the third equation. So let's see what we get. We would have our -3x plus 3x cancel. Multiplying the first equation by -3, we have -3y plus 4y, leaves us 1y. And for our z variable, we would have a -3z plus 2z, leaves us with minus z. And this is equal to, looking at our constants, if we take -3 times 3, we have a -9 plus 4, leaves us with -5. Now, at this stage, you might notice immediately that our second and third equation in this new system are identical. So we have two equations which are defining the exact same line in the YZ plane. So we're going to be working in the case that we have infinitely many solutions here. Now, one way that we could see that more directly, if we don't see it from the system that we have here, is to keep reducing our system by performing Gaussian elimination. So if I were to try to get rid of the variable y in my last equation, well, we notice that in our second equation, our variable y has the exact same coefficient of 1. So to eliminate the y variable in our third equation, we could take equation 3 and subtract equation 2. So our first equation is still the same. We have x plus y plus z is equal to 3. Our second equation is y minus z equals -5. And in performing this operation, equation 3 minus equation 2, well, we see our y minus y will cancel. Additionally, our -z minus a -z cancels. So we have 0 is equal to, on our right-hand side, we have the constant -5. Subtracting a -5 leaves us with 0. So our last equation becomes trivial. It simply says 0 is equal to 0, which is true regardless of our choice for x, y, or z. So at this stage, we're working in the case that we have infinitely many solutions, and to classify our solution, we're going to introduce a free variable. Now, before I make a choice for free variable, I'm going to simplify my system a little bit further. So this isn't necessary to do here, but one thing that we might notice is that the coefficient for z in our first equation and second equation are negatives, a +1 and a -1. So if I were to add those two equations, I could kill off the variable z, or equivalently, I see that they have the same coefficient for y, a +1 and a +1. So if I took their difference, I could kill off the value of y. So let's take a look at performing one more step to simplify. So the system that we have here is then equivalent to the system I get by taking my first equation, E1, and subtracting equation 2 from it, if I, say, want to kill off the variable y. So my first equation now becomes, well, we have an x. Let me use a different color here. We have a 1x, and then I'm subtracting 0x from the second equation. I have a y minus y will cancel, And then I have a z minus a negative z would be plus z. So I have plus 2 times z is equal to, well, I have for my constant, a 3 minus negative 5, or plus 5, leaves me with 8. My second equation is still y minus z is equal to negative 5. And my third equation is the trivial equation, 0 equals 0. So anytime that you're performing Gaussian elimination and you obtain the equation 0 equals 0, that is the trivial equation, we're going to be working in the case that we have infinitely many solutions. One of our variables could be chosen as a free variable. Now, the usual convention when you're making a choice for a free variable is to let your last variable, in this case z, be the free one. So here I might say let z be a free variable, and our choice for z let's denote as t, the same as we were doing before. So let's choose some number for z, let's call it t, be a free variable. So t can be any real number here. Now, in order, or once I make a choice for z, I have to be sure that I'm satisfying each equation that we have. So our second equation is y minus z equals negative 5. So solving that for y, I have z minus 5, or equivalently, t minus 5, since we chose z as our free variable. And then working with my first equation, I can solve for x in terms of z. So here I would see that x is equal to 8 minus 2z, or 8 minus 2 times t, where t is whatever value I chose for my free variable z. So here we have infinitely many solutions, and we would say the solution set is the set of all points x, y, z, where x is equal to 8 minus 2t, y is equal to t minus 5, and z was equal to t, such that t could be any real number. So here we have found our solution set, and the last part of this example asked us to interpret our solution geometrically. So what we see here is that these three planes in space have infinitely many points of intersection, and these equations, which we have found for x, y, and z, you might recognize from your Calculus 3 course as being the parametric equations of a line. So here, our solution set is representing a line which passes through the point 8, negative 5, 0, and is parallel to the vector v, whose components would be negative 2, 1, 1. So here, these three planes which we were given intersect in a straight line in space, so there's infinitely many solutions, since every point on that line would be a solution of our system. So in our last one, let's consider the same sort of problem to illustrate our last case for the type of solution we have. So again, here we are asked to solve the linear system of three equations in the three variables x, y, and z, and then interpret our solution geometrically. So we can perform Gaussian elimination to simplify this. So let me start by just rewriting our system. We have x minus y plus 2z is equal to 4. Second equation was 2x plus 3y minus z is equal to 1. And then 7x plus 3y plus 4z is equal to 7. So in this example, I already have that 1x coefficient in my first equation. That's my personal preference. I always like to have a 1x term in that first equation, which will then allow me to kill off the x variables in my second two equations a little more easily. So here, in my first step of performing Gaussian elimination, I would say that this system is equivalent to the system that we get by taking our second equation, that is equation 2, and subtracting 2 times equation 1 from it. So I'm doing that to get rid of my positive 2x. I would take my first equation, multiply by negative 2, so that I get a negative 2x, and then sum them. So I'm not making any change to my first equation yet. I've got the equation x minus y plus 2z is equal to 4. And then by performing this operation, let's see what we're left with. So we had a positive 2x minus our 2x cancel. Multiplying our first equation by negative 2, I have a positive 2y plus 3y, leaves me 5y. For our z coefficient, multiplying the first equation by negative 2, we would have negative 4z minus z, gives me a negative 5z. And then for our constant, we would have negative 2 times 4 is negative 8. Adding that to 1, we have a negative 7. And in this same step, I'm going to kill off the variable x in my third equation, that is my 7x, by taking equation 3 and subtracting 7 times equation 1. So let's see what that leaves us with. Taking negative 7 times our first equation, we have a negative 7x plus 7x cancel. Then for our y coefficient, negative 7 times our negative y is 7y plus 3y gives us 10y. And for our z variable, multiplying the first equation by negative 7, we have negative 14z plus 4z, leaves us with negative 10z. And then performing the same operation on the right-hand side, negative 7 times 4 would be negative 28 plus 7 leaves us with negative 21. All right. So in this new system that we have, we've reduced our second and third equations to 2 variables. So from here, if we were to eliminate one of those 2 variables, I get down to an equation involving a single variable. So one way that I might proceed is let's try to kill off the y term. So here I have a 5y and a 10y in my second 2 equations. So to get rid of the y in the third equation, I could take my second equation, multiply by negative 2 to get a negative 10y, and then add it to that. So let's see what we get here. This is equivalent to the system that we get by taking our third equation, E3, and subtracting 2 times the second equation. That is equivalent to taking negative 2 times the second equation, adding it to the third. So my first equation is still the same. I have x minus y plus 2z is equal to 4. My second equation is still the same. I have 5y minus 5z is equal to negative 7. And let's see what we're left with for our third equation when we perform this. So multiplying equation 2 by negative 2, we have negative 10y plus our 10y cancels. Then taking negative 2 times our negative 5z, we have 10z. Adding that to the negative 10z, we are left with 0. And then looking at our constants on the right-hand side, taking negative 2 times negative 7 gives us 14. Adding that to negative 21, we are left with negative 7. So at this stage, we see that our third equation is inconsistent. We have 0 has to equal negative 7, but 0 cannot be equal to negative 7. So as soon as we have some equation which cannot hold, we would say the system is inconsistent, which means that there is no solution. So here we do not have a solution of the system. And we're asked here to interpret what this solution means geometrically. Well, here we have 3 equations defining 3 planes in space. The fact that there is no solution means that there is no common point of intersection of all 3 planes. So we might say something like, there is no intersection of all 3 planes as a geometric interpretation. So in this first lecture, our first part of the section 1.1 material, we've introduced systems of linear equations, and we've seen that we can solve them by making use of this Gaussian elimination process, where we're performing one of 3 elementary operations to transform our system to an equivalent one, which is easier to solve. And we've seen through a few different examples that there are 3 cases for our solution set. Either we have exactly one solution, we have infinitely many solutions where we have to introduce a free variable to classify our solution set, or we have an inconsistent system which does not have any solution. Now, in the second part of this section, which we'll cover in our next lecture, we'll start making use of matrices to simplify this Gaussian elimination process a little bit so that it's not quite as tedious to write out from step to step.